Hello everyone, my name is Hoang Nguyen and I'm a senior at Portland State University studying electrical engineering. I'm also working as a research assistant at the Tusha Lab. Today I'm presenting on behalf of Peter Banda, Darko Stefanovic, and Christoph Tuscher on our project, Reservoir Computing with Random Chemical Systems. This project is funded by the National Science Foundation. So first, let me tell you what our project is and why are we pursuing this. On the left column is the traditional top-down approach of implementing chemical circuits, and on the right is the bottom-up approach that we choose to use. The top-down approach starts by specifying a particular chemical reaction networks, or CRNs, for a particular application. A CRN is a chemical system that consists of a set of species and reactions. Then particular species and reactions are explicitly designed in order to meet the specification of the CRNs or the application. The drawback of this is it's very application specific and hard and time consuming to construct. Meanwhile, our bottom-up approach starts by initializing species at random. These species will react among each other at random rates to create random chemical reaction networks. This approach targets at providing solution for a broader range of applications. The benefit is we can explore dynamical regimes beyond intuition and simplify adaptive biomolecular circuits. In our random chemical circuit model, we made a few assumptions regarding species and reactions. We have four types of species: upper strands, lower strands, full double strands, and partial double strands. Upper and lower strands are similar to the single-stranded DNA molecules such that only the opposite strand can bind together. The full double strand is similar to a perfect Watson-Crick DNA double strand, which all base pair of corresponding upper and lower strand are complementary. The partial double strand here is pretty similar to the full double strand, but only the substring are binding together. So these species, as I mentioned before, are reacting in these certain reactions. So the first reaction we have is the binding, where the upper and the complementary bind together to become a full double strand, or a upper and lower strand bind together to become a partial double strand. A displacement reaction happens between a single strand, can be upper or lower, and a partial double strand. In this type of reaction, the upper or lower strand displays a full complement to become a full complement, or a upper and lower strand being displaced by a stronger or longer partial double strand. Next, we create a chemical reaction network with those species and reactions. Here are the steps that we use to generate the network. First, we determine the number of upper and lower strands. In this case, we use a random generator, and I'm going to give an example. It's going to be 3 and 4 respectively for upper and lower strands. Second, we create the upper and lower strands as node. So I have a representation here. As you can see, U0 to U2 are the nodes for the upper strands, and L0 to L3 are the nodes for the lower strands. Thirdly, we determine the number of full double strands. In this case, I'm going to determine it's going to be 3 as our random generator. Next, we choose an upper and lower strand to become the full double, and we connect them with solid lines. In this example, it's going to be U0 and L0. So next, we take care of the partial double strands. For each of the upper strands, we determine the number of partial double strands, and our random generator gives us 3 for each of the upper strands. Next, we choose randomly the lower counterpart for each of the upper strands and connect them with dashed line. So in this example, For the node U0, we're going to choose L1, L2, and L3 as the counterparts, and we connect them with dashed line, as you can see. This process is then repeated with U1 and U2, and then we have 6 partial double strands in this particular chemical reaction network. 6, we impose ordering of partial double strands, and this is in order to the higher strand can display the lower order strand, but not the other way around. The highest order strand regarding to the more stronger or longer strands. 7, we choose random influx or efflux strands, and last but not least, we choose random rate constant, influx and efflux rate. As I mentioned before, we would like to implement reservoir computing in our system. Let me first introducing the concept. Reservoir computing is a machine learning technique that provides real-time computing on reservoir transitions without the need of the stable states. This method is very powerful in time series processing and prediction. A simple reservoir computer consists of 3 components: the input of the reservoir, the main reservoir, and the readout layer giving the outputs of the reservoir. The reservoir state is a fixed, randomly connected recurrent neural network that is high-dimensional filter with fading memory. The information in the reservoir state is then fed into the readout layer, and the readout layer is a single perceptron that reads the data from the reservoir states and uses feed-forward and backpropagation to map the actual output to the desired target by adjusting the weights. The readout layer is memoryless. Here we're interested in using our random chemical circuit as a reservoir computer. So the input state is the time-varying influx rate. The reservoir state is our random chemical circuit consisting of the time-varying species count of all the strands presenting in the chemistry during the stochastic simulation. These species react with each other through binding and strand displacement. The species count is then weighted with a uniformly distributed random number and projected into a readout layer, which we'll use to compute the output. In order to validate the performance of our reservoir computing model, we perform stochastic simulation of the chemistry for 1 second and let the readout layer take measurements throughout the entire simulation. The red arrow is going to move along the timeline, show the measurements taken by the readout layer. The plot on the left shows the influx rate as the input, and the plot on the right shows the output of an arbitrary task. So let me start the stochastic simulation. At a particular time, we start injecting a number of species into the system. And this is done by multiplying the initial influx rate or the base influx rate by a uniformly distributed random number R to create a new influx rate. And as you can see, the input and the output also change accordingly. We continue to take measurement and we hold and don't apply inputs for an amount of time tau. Tau is called the input hold time. After the amount of time tau, we apply the next batch of input into the system, as you can see here, which affect the input and the output change accordingly. This process is repeated for the rest of the period, and as we monitor through the input and the output, we can see they change according to the influx rate changes by the applying inputs. We also tested the random chemical reservoir computer with 2 time series learning problems, the short-term memory task and the long-term memory task. The tasks are the simplified version of the popular reservoir computer benchmark NARMA and require the reservoir to remember the past inputs. We use normalized root mean square error to measure the performance of the reservoir computer. For the short-term memory task, the reservoir computer is tested to remember the immediately past two inputs. The target of the short-term memory task is defined with the equation here. The left-hand plot shows the output and the target, and the right-hand plot is the mean and variance of the normalized root mean square error over 10 experiments. For each experiment, we also investigate how the base influx rate and the input hold time tau affect the error. It appears that the base influx rate doesn't make effect on the performance of the reservoir computer, whereas a better input hold time tau of 1 second, which is equivalent to more input applied to the network, provided to the chemistry, is more favorable for a better performance. Next, we bring it up to another level and we test it with a long-term memory task. In this task, the reservoir computer is tested to remember the past inputs that depended upon the input hold time tau. These past inputs are at tau second ago and 3/2 tau second ago. You can see the target is defined as the equation here. The left-hand plot shows the output and the target, and the right-hand plot shows the normalized root mean square error for 10 experiments. As similar to the short-term memory task, we're interested in seeing the effect of the input hold time tau and the base influx rate. And similarly, the base influx rate doesn't make a lot of effect, whereas a smaller input hold time tau is more favorable for a better performance. In previous work on DNA reservoir computing, Gudarzi and Yahiro have successfully used deoxide ribozyme oscillators to solve the two time series problems that I presented before. And these models are considered to be the state of the art. Here, we compare the best performance between our model and these two oscillator models. Our model achieved an 82% and 61% better performance than the Gudarzi's model, and 76 and 67% better than the Yahiro model, as shown on the plot here. I do want to mention that the most important trade-off of using our random chemical reservoir computer is the cost of implementation measured in the number of species. The model required 26 species, whereas the deoxide ribozyme oscillator OSSIs or reservoir computers only require 3 species. For future improvement, we can filter out the species corresponding to the node with negligible weights after training to reduce the size. So to conclude, here's what we did in our project. We used random chemical circuit model as a reservoir computer, and this model has outperformed the state of the art in solving the time series problems as demonstrated in the last slide. This model also has the potential to simplify the way we build adaptive biomolecular circuits, and we hope to have application in biomedical diagnosis and pathogen detection. Lastly, for future work, we plan to construct a more realistic DNA strand displacement circuit using Visual DSD, a Microsoft-supported tool for DNA strand displacement design, to validate the feasibility of this model. I would like to end my presentation by putting my information here. If you have any question, please reach out to me through email or the Slack channel, and happy to answer any of the questions. Thank you for listening.